Welcome to Chapter 8. In this video, we'll be expanding the ideas introduced at the end of Chapter 7, existing in a space where length is measured with the p-norm. To begin, I want to look at this graphic of some subsets of topological spaces. Put simply, a topological space is a space that has points, like the 2D plane, for example. Since we've been using the p-norm, we've been living inside a normed vector space. And since normed vector spaces are subsets of metric spaces, it means we're also in a metric space. The defining characteristic of a metric space is that it's equipped with a function that describes distance. Now, this is different from the idea of a norm because we want to be able to describe the distance between any 2 points, not just a point's distance from the origin. Nicely though, the distance between 2 points in a p-normed vector space is just the p-norm of their difference. This can also be seen in 2 dimensions as the p-norm of the change in x and the change in y. Visualized, every point of distance d from another given point creates a squircle with radius d from that given point. Additionally, you can see here that the line between the points is labeled with the same distance, and it's true that the distance from x to y is the same as the distance from y to x. Even if that fact isn't immediately obvious visually, it's much easier to show algebraically. Now let's apply this definition of distance to measuring arc length. When it comes to measuring the arc length of a curve, we can take an approach that you might be familiar with if you've taken BC calculus or a similar course. We'll call the distance between 2 points on the curve delta s, measured with the distance function. Delta s serves as our approximation for the curve's actual arc length on this interval. And as we increase the amount of subdivisions on the interval and start summing them, our approximation becomes better and better until it becomes the actual arc length of the curve. So this actual arc length is the p-norm of the differentials dx and dy. In rectangular coordinates, given a function in the form of y equals f of x, this looks just like the usual arc length formula, but with p's instead of 2's. The same goes for the parametric formula, but for polar, we have this lengthy formula. To have everything in terms of r base p and theta, I had to expand the derivatives of x and y, but because everything is to the p, it's impossible to expand this and simplify it like the Euclidean polar arc length formula. As a final note for these arc length formulas, I'm assuming that p is constant here. At this point, it would be too weird to consider changing the value of p while measuring consecutive p-norms, not to mention it would make our expressions that much more complicated. So along with these 3 arc length formulas, we also defined the distance function. I'll be putting a Desmos graph link in a pinned comment so you can play around with squircular coordinates and base p trig functions. Bye!